weighing a bucket of water or measuring a bucket of water and by weighing it, and then he put it outside, let it freeze, and then he weighed it again. They were the same. So heat was not a particle. If it was a particle, it was something that you should have been able to measure. You know, it was supposed to have some mass associated with it. So that you always have all these kinds of these theories that are out there. And this guy did that. And also the guy that was in the brewing factory, he wanted to refute what that chemist was saying. And so he was boring some metal inside of water. And he was looking at the mechanical energy that they was putting into it, and he was measuring the heat that was coming off of the water. He was looking at the steam and all of that stuff, and he compared it, and it was like 1 to 1. I mean, of course, you had some loss somewhere, but it was pretty much, if you could account for the loss in the wood, the heat that was just going to escape, then he was able to account for the loss. And he basically came up with the work energy theorem. So it comes out of thermodynamics, but we can use it in mechanical energy. You can see right here, we haven't even talked about thermodynamics. Okay, I haven't mentioned anything about heat or temperature. So when I start talking about thermodynamics, I'm talking about heat and temperature. Okay, although in a sense I have, but we'll talk about that later. In other words, temperature, absolute temperature, can be measured in terms of the movement of particles. So temperature is a result of movement. That's what we've now come to resolve. That as particles move more, the faster they move, the more, the temperature change would be greater. Okay. So this is what I'm going to do real quick. I'm going to go ahead and draw a couple of things here. Now I'm going to talk about Newton's law of gravitation. And this is where you have one body. Well, Newton's law of gravitation looks like this. F of G equals to big G times the mass of one body times the mass of another body, all over the distance of separation squared between those two bodies. So big G is the universal gravitational constant. M1 is the mass of object 1. M2 is the mass of object 2. And I have R up there. R is the distance of separation between the centers of the objects. So if I were to draw this, it would look something like this. We'd have one object right here. We'd have another object right here. This would be object 1, object 2. So you have masses. Those masses are associated with those objects. This could be considered the center of this object. So we have a distance between the centers here, and this is R. And one object will be pulled with a force of G. And when that object is pulled, oh, it don't look like you guys can see this. When this object is pulled, so basically M1 will be pulled by M2. Okay, so this is what this equation is saying. The force of gravity on M1 is going to equal to this, and it's by M2.